Hello everyone, welcome to Ground Zero. I have been thinking about what work looks like post AGI. I guess it will be less like grinding and more like choosing the problems that actually matter to you and a cross section of world. The thing is, researchers and builders are already living this. They are shaping experimental models, breaking paradigms, building tools that change how we work. But here's what keeps me up, the pace is insane. So much incredible work either gets lost in the feeds, never leaves the lab, or just disappears. The people doing the most interesting things often don't have the bandwidth or platform to show what they're actually building, and that sucks. So we are building signals on ground zero. It's pretty simple, an open platform for two groups, researchers and builders creating novel work, and founders shaping products that matter. The idea is to give you a space to show the real stuff, not the polished launch video, not the marketing tag, the messy parts, the pivots, the we tried this and it broke, so we did that instead moments. The technical trade offs nobody talks about because they are too in the weeds. You keep full ownership of everything. We are here to help more people see what you're doing. Publish a video content on Ground Zero YouTube. We'll help up with writings if you want it. Feature your work on the Ground Zero page. Push it through networks that actually care. And connect with the people working on the adjacent problems. The goal is exposure to people who get it, organic connections, and a place where experimental work doesn't get lost. If you're building something real and want to showcase to the community, we are here to support you out. Presenting your first guest on Ground Zero, Ali Behrouz. He's the a student researcher at Google Deepmind, and he's going to present three of his novel work: Atlas, Titans, and Nested Learning. See you.
Hello everyone, my name is Ali Behrouz and I'm PhD student at Cornell and also a student researcher at Google Research. And generally, I'm interested in how AI models can continually learn and shape a new persistent memory from what they have in their context. And also today I'm going to talk about three of the works that I have done over the past year. Generally, they focus on memory modules and how we can add long-term memory to LLMs, and generally how we can design LLMs from the first principle, and in order to make them continually learn and adapt to their context. This work has been a collaboration with Mason, Palin, and Wahab, and also other people in the group. And the main topic of what I'm going to talk about is about nested learning and what we call the illusion of deep learning architecture. And the stress here is on the architecture side, because in the paper, generally, we will discuss how we can translate the architecture into optimization problem, which has some benefits and help us to design more powerful architectures. So generally in this talk, I'm going to talk about the concept of continual learning, talk about deep learning architectures, as I mentioned, how we can add persistent or long-term memory to AI models, and also optimizers, and how we can view optimizers as a form of associative memory. And generally, the papers that I'm covering in this talk are nested learning, Titans, and also Miras framework. And you can find them on archive, all of them are on archive as well. So the main motivation that we were thinking about was, transformers are great, they can scale, and when we scale them, everything gets better, and they have revolutionized everything in AI. So basically, everything is great. Also, they previously the models that we had, basically they were some task-specific models, and now with transformers we can design more general-purpose systems, and so these systems are actually capable of adapting across a different task and context. So that's one of their main advantages. But also there are some missing points and aspects in these models, And so, for example, one of them is about long context efficiency. Transformer structure has quadratic costs. We cannot scale their context. And so if we want to somehow achieve the infinite context, we need to somehow overcome this quadratic cost. And another thing is that they do not have a proper way to capture different levels of knowledge abstractions. And it's very important for their understanding of the context and everything like that. They're not robust, and they cannot adopt fast. And also, finally, the most uh, important one, in my opinion, is about continual learning. And when I'm talking about continual learning in humans, humans can continually learn. And when we use that term, it means that there is no test time, there is no training time. And so when there is no test time, it means that there is no we cannot say that there is a training process in the test time or something like that, because there's no term about both training and test. And the model is continually shaping new memories, and it's shaping new levels of knowledge abstraction, and so on and so forth. So that's the main goal of this process. So you know we need to better understand what's the main advantages of like humans that I mean, they can do this continual learning part. They can always learn. And why LLMs cannot do that, what is missing in their structure or generally architecture. And I want to use an analogy about like how uh, generally like the current models are missing some important concepts. What I'm going to talk about is about one condition in human, which is like anterograde amnesia. And so when this condition happen, after the onset of this condition, the person cannot shape new long-term memory, but previously stored long-term memory are unchanged, and the person has access to them. So the person knowledge is limited to the long-term memories that are shaped before the onset of this condition, or the present. So the person experience the present as it has always been new. And in the general process, there is no transfer between the short term and the long term memory of that person. So the interesting thing about the anterograde amnesia is that the short-term memory of the person is there, and the long-term memory of the person is also there. But unfortunately, there is no transfer, there is no knowledge transfer between the short-term and long-term memory. And the interesting part, in my opinion, is that when we look at LLMs, we can see that the current like design of LLMs usually have some knowledge cutoff. And in order to like make them more capable of understanding new knowledge, we need to, for example, fine tune them or retrain them, or all their things, which might be very costly. And the model cannot naturally learn from the data over time. And also, similar to anterograde amnesia, we can see that their knowledge is limited to two parts. One is the part that they have learned over pre-training, and another one is about the immediate present or their context. So it seems that the main issue here is that there is no connection between the immediate present and also their pre-training knowledge. And so the question is how we can make this happen, how we can make the model more capable of doing this continually learning process. And so in order to like answer all these questions, the first thing, in my opinion, is to understand how we can learn and memorize, and how the LLM can learn and memorize. So we need to like discuss one important background concept, which is associative memory. So in general, associative memory is a fundamental for the learning process of human. And so it's the ability to remember the relationship between, related or unrelated events. For example, when we match the name of a person to their face, then that's a form of associative memory. And so, from the technical point of view, we can think of associative memory as a dictionary. We have keys and values. We want to map keys to values. But the point here is that there is no predefined mapping from the model perspective. And so, the model needs to learn how to map keys to values. So in the training process, as I mentioned, for the model, there is key and value. And when we want to do inference, then we have query parameter as well. And the model, based on the mapping between keys and values, needs to decide how to, shape the output that is corresponding to the query we have right now. So that's the general process of associative memory. And, as I mentioned, the process is somehow a learning process. And when we have a learning process, we need to have an objective. So somehow it can measure the quality of the learning. And also we need to optimize that objective. So formally, we can define associative memory as follows. So basically, if we have keys and values, then we assume that they're given, and the associative memory is trying to learn a mapping between keys and values, and there is an objective for that. This objective generally measures the quality of the mapping, and M here is the function that we want to learn. So that's a learning problem. So just for just as a something as an example for this learning process, we can have different objectives here. For example, let's say that M is just a linear mapping between keys and values, and then it seems that the problem is like a regression problem. We want to, we have keys and we want to map the keys to values. And so one simple objective is dot product similarity between the predicted value and also the actual value that we have. So here in the left-hand side, we have this dot product similarity objective. Or, for example, we can use L2 regression loss that minimize the difference between the predicted value and actual value that we have. So later we discuss more about like how we can use these objectives to design powerful associative memory. More specifically, I will use the dot product similarity one as an example for both architecture and also optimization side. So now let's go to the next step. For this process, let's first focus on the architecture side. And I'm going to just like talk about a preliminary example. So as we had in the previous slide, we have this associative memory. We want to map keys to values. And with different objectives, we can have different quality of mapping. So let's say that we want to choose this dot product similarity, and we want to use gradient descent to update this objective. And again, assume that the keys and values are already given. So using gradient descent with also like weight decay, what we have here is that mt, the state of m at time t, is equal to alpha t times mt minus 1 minus the error in the gradient descent. And if we take the gradient from this objective, what we'd get at the end would be the simple linear attention formulation, or the recurrence corresponding to linear attention. So from this perspective, it seems that linear attention is a form of associative memory, in a way that it tries internally it tries to learn a mapping between keys and values. Another example is about L2 regression loss. So instead of dot product, we now use L2 regression loss. And again, in the most simple way, we use gradient descent as the optimizer of this optimization problem. And again, if we take the gradients and just substitute this term, we will get this update rule that we have here, and it actually is equivalent to the delta rule. And so that's another like update rule that we can have for the architecture or the memory that we have. So just as a visualization process, let's consider the first example that we just talked about. Objective would be a dot product similarity, and we want to optimize it using gradient descent. And so, as I mentioned, it basically is equivalent to the linear attention. But here we change the process a little bit. We assume that the initial state of the linear attention, because if we just expand this recurrent formula that we have here, at the end we will need to also like have a term of M0, which is the initial state of this learning process. And what we want to do here is that we want to meta learn the initial state of this linear attention. And so in that sense, the M0 is optimized in the outer loop. So in the outer loop, what we have here is basically just a 3 linear projection. So the input comes, we have the projection of query, keys, and values, and then we go to the inner loops. So what happens in the inner loop is that we are trying to learn a mapping between keys and values. So we have like 2 levels here. And then we have 2 types of parameters in the problem that I mentioned. One is the initial values of the memory, which is just a linear block here. And another one is the recurrent formula that we have in context. So it seems that the initial parameters are trying to compress the general knowledge about all the context in the pre-training. But on the other hand, the inner loop part is trying to adapt to the context using some steps of gradient descent. So when we look at the problem in this way, we can see that the linear attention is a form of 2 levels of optimization problem. One is the pre-training process, and another one is the adoption of the memory to the context, which is a form of associative memory. So using this intuition, we designed Miras framework, which is a general framework for designing new architectures. And we argue that for designing a new architecture, you need to take 4 design choices. One is the memory architecture. Do you want your memory to be a vector, matrix, or a deep neural network, or generally any kind of architecture? So this memory architecture somehow is trying to compress the context into its parameters. So the more powerful the architecture is, the more powerful memory you have. So that's generally the process. And the second one is the objective, the internal objective that measures the quality of the mapping, which we call it attentional bias. So you can use different objectives here and design different architectures. So that's another design choices. Another design choice is about retention gate. How do you want to retain the knowledge that you had in the previous state? Do you want to have gating? Do you want to have like forget gate, or do you want to retain all the information that you had in the previous state? So basically that's another design choice. And finally, the point is like, how do we want to learn the internal process? Do we want to use gradient descent as we discussed in the previous slides, or do we want to use more more powerful algorithms like gradient descent with momentum or Newton's method, or even like non-parametric solution. So that's another design choices. So based on all these design choices, we show that most of the architectures, or generally like the more popular architectures, are a form of this Miras framework, are an instances of this Miras framework. For example, as also like discussed in the previous papers, softmax attention is a form of non-parametric solution to this regression loss, where the kernel S is basically just the exponential of the dot product similarity of qi and ki and q. So we can see that the non-parametric solution to this objective is basically the softmax attention that we know. So another example that we discussed was linear attention with Hebbian rule. So if we use dot product similarity, then if we take the gradients, it would be the simple version of linear attention. Or we can use L2 regression loss and assume that, for example, the memory is just a matrix, and then we can come up with the delta rule, and that's another way to define the recurrence of the model. Or, for example, in Titans, that I will talk more about that later in the talk. For example, if we use the same L2 regression loss, but instead of a linear matrix, use a deep neural network, and also add weight decay, and instead of optimizing the process using gradient descent, we optimize it using gradient descent with momentum, which is more powerful optimization process. Then the resulting architecture would be the long-term memory module, the update that we use in the long-term memory module in Titans. And so in the literature, there are like more powerful learning rules as well. We can go to, for example, the Oya rules tries to improve the Hebbian rule that discussed in the previous slide by adding this regularization term. If we optimize this L2 this objective, then we will come up with the Oya rules. That is another form of like Hebbian rule, the improved version of the Hebbian rule. Or, for example, in Omega rule, we can have basically what we have here is just like objective agnostic. For any objective, what Omega rule does is that instead of optimizing the current state of the memory with only the current input of the keys and values like ki and kt and vt, it optimizes the memory with respect to the, for example, a local window of the past keys and values. So basically, it's not a form of online learning anymore, and it requires caching the previous keys and values, at least some of the keys and values. And based on this, for example, this learning rule, in the most simplest way, if we use the same objective as Hebbian rule, which is just the dot product similarity, we can come up with the sliding window linear attention. Basically, instead of just updating the memory with respect to the last vi ki, we can update it with respect to a past set of keys and values. So that's another learning process. And I don't want to go through all of the architectures, but generally what we have shown in the Miras paper is that most of the architectures that we know of are a form of associative memory, and we can somehow represent them as some nested optimization problem. And now let's go to the optimization side, optimization algorithm, and generally backpropagation process. And again, I will start with just a simple preliminary example. Let's say that we have just one linear layer and we want to train it on the data sets D that we have. And the loss function for this training process is L. And it's just a supervised learning process. It tries to map xt to yt. And so let's say that we want to optimize this process using the simplest optimizer, just simple gradient descent. And if we simplify the process using chain rule, what we have is this recurrence formula for updating the weights of the model given the data sets that we have. And xt is basically just a batch, or generally one data sample from the training data sets that we have. Now let's say that ut plus 1 equals to this gradient term we have in the chain rule. So if we like use this term, then we can simply show that one step of gradient descent, it's actually well known that one step of gradient descent is equivalent to this optimization process. So if we optimize this, find the solution for the argmin of w that can optimize this objective, then the solution would be just one step of gradient descent. And the interesting part here is that you can say xt plus 1 here is just a key, and ut plus 1 is a value. And it seems that we are training an associative memory in the way that the backpropagation process is a form of associative memory that is trying to map keys, which here is the data sample, to the error rate in the backpropagation process. Here is the ut plus 1. So it seems that the backpropagation process itself is a form of associative memory. So I'm not going into the details of the, all the math part here, but generally in the paper, in the nested learning paper, we show that we can go like beyond just one simple linear layer that I just discussed for any like backpropagation process. If we let delta to be the error of the backpropagation for the layer L, and also assume that the x hat is just the input of the layer L, then we can show that again, each layer is a form of associative memory that tries to map its inputs to the error rate that it receives for the backpropagation process. And so generally the backpropagation process is a form of associative memory, but it's a little bit like different from the linear attention that we discussed, because in the linear attention, we know that the keys and values are given. But here it seems that the process is a little bit more complicated, because this delta L that we have also depends on the previous state of the memory, or WL, that we have here. I will discuss more about like what are the differences between gradient descent and linear attention, but generally for now we can just assume that the backpropagation process is just a form of associative memory. And now we can go beyond that. For example, let's say that instead of gradient descent, we want to use gradient descent momentum. And the interesting part here is that momentum itself is a form of associative memory for gradients. So it seems that momentum is just compressing the gradients, and it's not just, we shouldn't just simply look at the momentum as an exponential average of the gradients. We can go to more complicated process to define momentum term, which I will discuss more in the coming slides. Again, as I mentioned, linear compression, or generally linear attention, is different from gradient descent. In linear attention, keys and values are given, and the model itself only needs to learn the mapping. There's nothing else to do. And the process in linear attention, because all the keys and values are given, the process is parallelizable and very fast, and generally the memory is just a simple linear memory. But on the other hand, in gradient descent, as I mentioned, the value is generated by the model itself, because the value depends on the previous state of the weight or the memory that we have. So these models in the literature are called a self-referential model. self-referential model are the models that refer to themselves, and somehow they can learn their own update rule. And here, the gradient descent is trying to generate its own value function, the value in the memory. And so it's a form of self-referential process. And so contrary to the linear attention, which only learns the mapping, now the model is trying to learn first how to generate the values, and second, how to map keys to the generated values. And another thing about gradient descent is that this recurrence that we have is not non-parallelizable, and it's non-linear by their nature, by its nature. And so these are the main differences between linear compression and gradient descent. And intuitively, it seems that gradient descent, due to this self-referential processes, is very more powerful than a simple linear compression process. And it's actually a motivation for us later in the talk to design a self-referential Python process instead of just a simple recurrence. So what we have learned so far about optimizers is that backpropagation is a form of associative memory. And when we look at that from that perspective, we can say that pre-training is a form of in-context learning, when the entire context is the entire pre-training data, and the model is trying to compress the context into its parameters. And so it's a form of in-context learning. And another thing in the paper we discuss is that all other optimizers that we know, for example, Adam, Adagrad, mu1 optimizer, all of them are the form of associative memory and can be written as some nested optimization process. So I'm not going into the detail of all the maths about like how we can write them, but you can find them in the paper. But generally, the main intuition, for example, for Adam or Adagrad, is that the model is trying to learn a mapping between the current gradient and global information about the about all the past gradients. Generally, learning this mapping using L2 regression loss and finding the optimal solution would result in Adam or Adagrad, depending on the operation, whether it's element-wise or in the matrix format. So that's generally how we can write more complicated optimizers as a form of optimization problem. And so why it's helpful, because we can go beyond the current definition of, for example, gradient descent or momentum. And here we have just two simple examples that we can go beyond the current algorithms. For example, in gradient descent, as we discussed, is just a L dot product similarity of W and WXT. Here xt is the inputs and also the error rate in the backpropagation process. But instead of L2 regression loss, for example, we can use, instead of dot product similarity in the gradient descent, we can use L2 regression loss and then come up with this delta gradient descent that we present in the nested learning. Or, for example, similarly, for the momentum term, you can use L2 regression loss and come up with a new update rule for momentum term. And so it can be potentially more powerful. I will discuss more about that later with some examples that why these formulations can be more powerful. And now let's just put everything together. So far, what we have seen is that architecture side can be reformulated as some nested optimization problem. And on the other hand, optimizers are again a form of optimization problems. And when we look at deep learning, or what we usually use and how we define the architecture or optimizer, we are only seeing the final solution to all these learning problems. But if we look at them from the nested learning perspective, then we can see all the internal learning process in all these modules or blocks. And why they're important? because basically we can design more powerful architectures when we can control their learning process, or we can somehow generalize them, as we discussed later in the talk. I will talk about continuum memory system that somehow builds on the intuition of this nested learning. So in order to like formally define nested learning, we need to first define update frequency. So in general, we have a unit of time, which generally we can say that it's just the slowest frequency of update among all of the blocks. And just one step of the update for that block is considered the unit of time. And then for any other components, we can define the update frequency as the number of time that we update the parameters, or generally how we fit to the context it has. So just a simple example here is that if you have a recurrence model and you have a context length of L, then the frequency update for that model is just L, because the unit of time is the outer loop or the pre-training process. So for each document that you have, you need to take L steps for your recurrent models to go through all of the tokens. And so the outer loop has the update frequency of 1 because it's the unit of time. And the inner loop, which is the RNN side, has the update frequency of L, which is the context length you have. That's just one simple example. And now based on this update frequency, we can say that A component is faster than a component B if the frequency of update for A is like larger than the frequency of updates in B, or the frequency of update is the same, but the computation of B depends on the computation of A. So just one simple example here is that if you look at the gradient descent and momentum, you can see that the frequency of updating gradients is the same as the frequency of update in momentum term, but in order to update the weights using the gradient descent, we need to first compute the momentum term. And so from that perspective, momentum is a slow parameter, and the gradient itself is just a fast parameter. The gradient itself is a form of a slow parameter, and the momentum is a form of fast parameter in the optimization process. Or there are other examples. For example, when you have meta learning, you have like bi-level optimization process. The outer loop is just a slow network. The inner loop is the fast network. And again, in attention RNN or momentum that we discussed. So all these are just some simple examples of how this update frequency can be defined. And now let's go to the second definition, which is a nested system. So I'm not going into the details of how we can formally define nested systems, but in general, intuitively, what we have is we have some blocks, and each block has its own gradient flow, and each of them are trying to locally solve a new problem that we define based on an optimization process. And each of the blocks has its own parameters, its own context, and also its own objective. So these three are the most important components of defining a nested system, and that's generally the process. And based on the nested system, we can also define nested system of associative memory, where each of the optimization process are a form of associative memory that is trying to map keys to values. That's the general formulation we have for nested learning. And you can choose any form of optimization process you want for optimizing each of these blocks. And if it's gradient descent, then it's not decomposable. But if it's, for example, more complicated optimization process, you can again decompose that optimization process into some levels of nested learning, and where each of them are optimized based on gradient descent. And So far, we define how we can have a nested system of optimization problem and how we can translate a neural network and its optimization process, learning process as a form of nested learning. But the question is how we can transfer the knowledge, how we can pass the knowledge from one level to another one. And here I want to discuss some examples. The first one is direct connection between levels. So the output of the slow, right now I'm just talking about like two levels. We can go beyond two levels, but that's just a simple extension of what we have here. So for the sake of simplicity, I only talk about two levels. So we have one slow level and one fast level. And one simple way of knowledge transfer is through direct conditioning of the output of the slow network on the output of the fast network. So that's one way. So example of this process is basically just the linear attention that we discussed. So all these parameters of projections that we have, projections of Q, K, and V, are in the outer loop or a slow level that we have. And then in the fast level, we can have the linear attention or attention. And so it's just a fast network we have. And the final output is just a simple multiplication of the memory and Q. So how we obtain Q is based on the outer loop. So generally this process is computing is computed in the outer loop, but the state of empty is computed in the inner loop. So we are conditioning the computation of the outer loop based on the computation of the inner loop. So that's one way of knowledge transfer. Another way of knowledge transfer is non-parametric way of direct or conditioning process. So the example of this would be attention in transformers. So we don't have any parameters, but the output of the general model depends on the context in the inner loop of the attention. So that's another example we have. Another thing is that, when we have a deep neural network, then each layer has a, initial layer are in like upper level because the computation of the later layer depends on the computation of the initial layer. So how we, perform this knowledge transfer between different levels or different layers in this case, is through backpropagation. So backpropagation is another form of knowledge transfer between levels. And another thing is, for example, when we have two levels, the slow network can learn the initial state of the fast network. And so it's equivalent to the model agnostic meta learning. So you can simply just generalize this process to multi-levels and go beyond that. And so the knowledge, another form of knowledge transfer is through initialization. Or we can go to other form of knowledge transfer. There are a lot of ways. And, one thing that we wanted to advocate for here is that, we need to think more about how we can do this knowledge transfer. And we shouldn't just limit ourselves to the knowledge transfers that we know of. So another form is basically through the generation. We can say that a model is generating the weights for another model, which is equivalent to hyper networks. Or if we think about the levels corresponding to the optimization process and the levels corresponding to the architecture side, we can see that the context of the architecture side is token, but the context for the optimization side is gradients. And the context of the optimization side, which is gradient, is generated by the architecture because it depends on the architecture that we have. So from that perspective, one thing that we can say is, architecture is generating the context for the optimization process. And so it also gives us this intuition that how we should design more powerful optimizers and somehow make them dependent on the architecture. Let's go through some implications, like how this perspective and what we have discussed so far can help us So some parts are just like we already have discussed about them. For example, we can go beyond dot product similarity and define, for example, delta gradient descent, delta momentum, and we have other variants, for example, momentum with deep structure, and so on and so forth. So there are like different ways to generalize the optimizer that we know of. So that's just one implication. Another thing is, as I mentioned, is the intuition that optimization process, the context for optimization process is generated by the architecture. And there were some like previous evidence about, for example, transformers cannot be trained, I mean, in a good manner by simple stochastic gradient descent. And so this gives us some intuition about like what's going on, because it seems that the generated gradients by transformers are too complicated, and so the gradient descent cannot like compress those complicated contexts into the parameters of the model. So we need to use more complicated optimization process in order to manage the memory and somehow compress the data. So this intuition motivates us to think more about architecture dependent optimization process. And another interesting part, in my opinion, that I personally really like is when we think about continual learning, then the long context understanding is also very important for optimizers, because the optimizer itself is trying to find the effective solution in the loss landscape. And in order to do that, it needs to understand a global property or characteristics of the loss landscape. And for doing that, it needs to somehow have access to more and more steps of previous steps of the gradient descent that we have performed. So generally, this long context understanding can help the model to somehow find the effective solution in the loss landscape. And finally, like to show that how like this intuition about delta momentum or delta gradient descent is important, and how we can this new design can help us to find the effective solution. We have a simple optimization example here. So we are trying to optimize this objective we have here, which is very complicated because there are a lot of like changes in the loss or the function. And so we perform this toy example, a toy optimization process, and we observe that like standard gradient descent with momentum can simply fail to find the effective solution or the optimal solution, but our presented delta momentum can simply just find it very fast. And so that's just one toy example to show that how these models can, these designs can. Another implication, as I mentioned, is about self-referential Python process. As I mentioned and discussed about like gradient descent and linear recurrence, we can see that linear recurrence is like less effective, because it only learns how to map given keys and values, and it doesn't have any control about like its update rule. But when we have a self-referential process, the model generates its own values for the memory. And so it has more, flexibility to learn more complicated mapping between keys and values. And that's just one goal for self-referential Python model. And another thing is that in Pythons, we have like learning rule, we have weight decay and all these things. So usually what people do is that they make these parameters input dependent. So in order to do that, we need to project the inputs data into the learning rate or weight decay of the inner optimization process of the memory. So generally, the main issue with that is all those projection layers are fixed, very similar to ML blocks. All of them are fixed. But here in self-referential Python, we want to make every single part of the model adaptive. So everything is changing based on the context, and also it's updated through the context. So there is no like fixed uh, fixed and persistent block in the self-referential Python module, and everything is changing, adaptive, and also self-referential. So the way it works is that all the projections that we usually have for a sequence model, all of them are placed in the inner loop. So they are changing based on the context. So we are updating them for each step. And also the value, as I mentioned, is generated by the model itself. And so the recurrent formula is just basically the optimization process of L2 regression loss between projections KT and the learned value of the memory. So that's the general process. And so in the self-referential Python, the design choices that we have in the formulation above is that we use L2 regression loss instead of the objective of L here. And also to optimize that, instead of a simple gradient descent, we use our own delta gradient descent with moments. And so generally the update rule for each layer of Python, when the memory is just a simple linear layer, would be something like this formulation that we have here. And so in the experiments, instead of a linear layer, we use 2-layer MLP, which make the model more expressive and also with more capacity to compress the context. And so based on this self-modifying Python module, we present Hope architecture. So the main intuition of Hope architecture is that it uses self-modifying Pythons, but on the other hand, instead of just a simple MLP blocks, it uses a continuum memory system that we present in nested learning. So what's the intuition behind that is, let's say that we have a pre-trained transformer, and the transformer block or the attention block seems to have infinite frequency because basically it's parallelizable and can fit the context as in just one step of time. And so it has the frequency of infinity, but on the other hand, we have MLP block after that. And the MLP block is just simply, has the frequency of updates of 0 because we don't update it after the pre-training. And so it seems that we have like two extreme cases, one with infinite frequency, another one with 0 frequency. And so we can have like multiple MLP blocks. Each of them are optimized based on its own frequency of update. And why it's important? Because it provides a loop structure in time dimension. Why it's that? Because the high frequency feed-forward network can simply forget because we are updating it more often, and it can face catastrophic forgetting. But at the point it faces catastrophic forgetting, the knowledge is still there in the mid-frequency or low-frequency levels. And so through the back propagation, that knowledge can come back to the high frequency feed-forward network that we have. So if we have a piece of information which is very important, then the model would not or hardly forget about that. And so that's generally the Hope structure. We have self-modifying Python followed by a continuum memory system. So now I'm going to talk about the experiments. And so in the experiments, we have some, standard language modeling and common sense reasoning tasks. The point here that I want to mention is all these tasks are local. So when we are talking about continual learning, And when we are talking about like long context understanding, the improvement for the model would not be like that much, because all these tasks are local and more requires like more parameters to get better results. But the point of these experiments is that to show hope is just a strong backbone, and it performs well on all these language modeling, common sense reasoning tasks. But when we go to, for example, long context task, or for example, more recall intensive task, we can see that modern recurrent models and also like Titans fail, for example, in this recall intensive task that we have, and hope can somehow close the gap of recall intensive task with transformers and perform better. But again, all these tasks are just about like the expressiveness of the memory, how it can compress the data, which again, Titans also like have deep memory, is like using a very powerful memory update process. And so basically it also like show good results. But now let's go to a harder task. For example, here we have the Babylon in the right-hand side. We have the Babylon benchmark, and generally it's a form of needle in haystack. So we can see that, for example, a model like Titan would fail after like 2 million tokens in the context lengths. And but the interesting thing is Hope architecture can perform very well, like more than 90% when we have 10 millions of tokens in the context. So generally it's very effective for longer context. And also when we look at the loss or the perplexity with different like context usage, again we can see that Hope is very effective for using the context it has. And so it shows the powerful memory management that it has. But now let's go to even harder task, the continual learning task. So the task that we have here is just a continual translation of a novel language. So we have two languages they have not seen in the pre-training. And so the task is we pass the vocabulary and also grammar to the model in context, and then we ask that to translate the queries to English, queries document to English. And so we have two setups for that. First is the red points. In the red points, basically, we just use one language in context. And we can see that both in context learning and also Hope with different levels of continuum memory system are just like working fine. So that's just the baseline we have. Now let's go to the continual setup when we have both of these languages in the simultaneous manner. And the model needs to understand both of them and then translate the queries in each of the languages to English. And so in this setup, we can see that in context learning basically fails. And so with more levels of continuum memory system, we can recover the process of non-continual, we can recover the performance of non-continual learning setup. And so it shows that with more levels of continuum memory system, we can have better and better long context understanding. Another task that we focus on as just a form of ablation study on the on having different levels of in context learning is just some incremental classification task and also like question answering task. And here what we have is we have the in context learning as the baseline, and we use like more and more levels of continuum memory system or generally in context learning capability. And we show that with more levels, the performance of the model, the accuracy of the model can get much better. or generally the perplexity can get much better. And so it also shows the importance of having multiple levels of in-context learning. Thank you very much for your attention. And here are the references that I use in this talk. And yeah, thank you.